Thank you, Neil McKinnon and the Royal Society of Tasmania, Northern Branch, the committee members and its members for the invitation and privilege to present today. Thank you too to QV Mag for the venue and their support while preparing for today. Bob and I would like to acknowledge the Palawa and Pakana people as the traditional and ongoing custodians of Lutruwita. We pay our deepest respects to the elders past and present and acknowledge Tasmanian Aboriginal people who are here today. Today's presentation is a comprehensive geological origin story of the Tamar region. This is a 5-year project of Bob Cotton's. I have had the honour of being asked by Bob to lend my voice to his words and to his work to be published in the papers and proceedings of the Royal Society of Tasmania, volumes 159 to 2025. It's called New Perspectives on a Cenozoic History of the Tamar Valley and Launceston Gorge. So why is this story important? After today, we hope you will see a new dimension to the Tamar region and have a new sense of place, a new understanding of how the geological origins continue to shape the lives of the people in the region today. The presentation comes in 2 halves. The first half is the story, and the second half is for your questions, which Bob will aim to visually illustrate the answers to those questions. We will cover the period from 180 million years ago through to today. And I promise today's presentation won't take that long. So here at Launceston's fabulous QV Mag, we actually sit right in the middle of the study. The study covers an area of over 4,000 square kilometres of the Tamar and the North Midland regions, bounded by the central northern coast, by the eastern and western tiers, and to the south, the township of Poatina and Nile. The Tamar today is a tranquil landscape. It was not always so. Great geological events fractured, filled, and eroded the landscape. We are talking millions of years ago, often denoted by that symbol MA. As you hear about these events today, we really want you to visualize the physicality of it all. This first image is of Antakya Rift Valley. It was recently created in all of 2 minutes by a mega earthquake. It took many of these to make the Tamar Rift Valley.
The local people said that at the time they thought it was an air raid, the sound of explosions created by cracking rock, the flashes by the sparks that flew as the Earth's crust was torn apart.
There were great waterfalls, powerful rivers, and floods of dolerite clay conglomerates, which you can see today in the landscape. And of course, volcanoes spewing molten lava. So here's a tip to help make sense of all these great geological events. Look at the impact of the flow of water, redirecting, raising, and lowering and flooding watercourses. So through this presentation, watch how each event impacts that flow of water. So let's get into it. From where we sit and look towards Mount Barrow, Mount Arthur to the eastern tiers, it's dolerite. When we look towards Hagley and Poatina, to the western tiers, it's dolerite. Where did this come from? Well, this being an origin story, it starts at about 180 million years ago in the Jurassic period when Australia had dinosaurs roaming and an inland sea. During this time, Australia was separated from Antarctica and Tasmania was being caught in between. Then molten dolerites began to intrude between flat rock layers throughout the east of Tasmania. These first molten dolerites are a sign of the coming breakup of the supercontinent Gondwana. These gradually cooled to hard rock in masses hundreds of meters thick. The pristine 170 million old dolerite was undeformed and probably sat at about 300 to 400 meters above present sea level. This connected the Mount Arthur, Mount Barrow, Ben Lomond terrain at about 1,500 meters above sea level, with the Western Tiers terrain at a very similar elevation. So let's change our view. Here's the Tamar region, but now looking southwards. From Georgetown at the bottom near Bass Strait towards Evandale at the top of the screen. 100 million years ago, the Tamar dolerite was effectively a slab of 300 meters or so thick. Probably was slightly dished between Longford and the Western Tiers on the extreme right. Fault lines through this dolerite slab ripped 50 kilometres or so inland from the New Bass Basin. Great loosened blocks of dolerite sunk under the gravity, forming the floor of our valley. Less affected blocks formed steps of 50 to 100 metres or so, creating valley walls. All of this was in dolerite rock. The result? A rift valley. To the west was a very large fault-bounded depression in the dolerite, 20 by 50 kilometres now, called the Longford Basin, with a very deep rift developed south of the future Hagley. These structures underline the present northern Midlands. Now exposed to the atmosphere, the upper surface of the dolerite started to oxidise, the start of a long, gradual weathering process. These two troughs stood ready to receive water and sediments. Plenty of sediment was available from weathering and erosion of the surrounding dolerite tiers. About 50 million years ago, one of the faults went deep enough in the north in the Rowella Hillwood area. Let's zoom in. That fault went deep enough to tap molten rock. The basalt lava flowed to the surface and erupted through volcanic vents. Periodic earthquakes shook the new valley, and with each pulse of molten rock, lava flow built on lava flow out to the valley walls. Even now, it is possible to start at Batman's Bridge and cross the valley entirely on basalt. With the valley walls confining the flows, the lava pile grew over 100 metres high. Some water overflowed the dam, continuing on across the dry terrain of Bass Strait. However, its sediment load was trapped, accumulating upstream of the Batman volcanic dam. Let's zoom out to see the impact of that water being trapped. The water continues to rise behind the volcanic dam, and water is also being caught in the Longford Basin. So as we watch these waters rise, keep your eye on the top right-hand corner as those two filled spaces become one great big single first lake. And there they are, crossing that saddle or horse. The basalts of Batman Volcanic Dam finally reached a high enough level to hold back water and sediment to 140 metres above sea level. The lake reached from Batman Highway over the future Launceston and under the future Avondale, then beneath the future Longford, reaching halfway to the Western Tiers. While the first lake had reached its 140 metre maximum in the adjacent high-level dolerites either side of Avondale, deep weathering was forming masses of clays surrounding large dolerite boulders. That weathering was already weakening the Batman Volcanic Dam. Let's zoom in for a closer look. On the west edge of that volcanic dam, you can see it being cut by water escaping. This first lake was starting to drain. Now, let's see the impact of that draining by zooming out. With that draining, the vast 140 metre high sediments were revealed. New river courses emerged and all converged with the North Esk to make a new proto-Tamar River. And this flowed straight into the head of the Tamar Valley under the future Avondale. Now, this approximately 37 million year ago is a pivotal moment with a lot going on. But remember, at this stage, there was no Cataract Gorge to receive rivers. The gorge was still solid dolerite. So we'll unpack this slowly. Again, watch the impact on the flows of water. The dolerite clay conglomerates, shown in dark purple, patches are in motion down the slope towards the Tamar near Avondale. Grindelwald, Cocktail Hill, Stromboli volcanic vents begin to erupt. At the Batman Dam, basalt flows had come out on top of the first lake sands. And without warning, above Whirlpool Reach, there was a catastrophic failure of that first volcanic dam. The powerful flow of the escaping lake water rapidly scoured loose the sand supporting the basalt sheet 140 metres up. Parking lot-sized blocks, slabs of basalt slumped to near sea level. Okay, let's investigate that collapse of the Batman Volcanic Dam and its impact. Here, that failure triggers a rapid erosion phase in the loose sediments behind the dam. A V-shaped valley was rapidly gouged, retreating upstream. A split in the valley left behind the basalt-capped Windermere Ridge. This is the Tamar Valley. So let's go and focus now on the conglomerates movement and its impact. Great masses of dolerite clay conglomerates were on the move. moving down the slope towards the Proto-Tamar River. One mass arriving from the east was impacted by and mixed with the basalt lava flows from the Stromboli volcano from the west. The masses collided on top of that 140-metre first lake surface into the bed of the Proto-Tamar River. The combined volume catastrophically blocked the fast-running river and continued to build up higher into a second new volcanic dam. The river waters naturally immediately started a new second lake upstream of the Avondale and towards Longford. You can see how the lake is fed water and sediments by all the North Midland rivers of the time, steadily rising upstream. The rivers are being subsumed into the second lake. And critically, we can see how the second lake covers and buries that 140-metre sands of the earlier first lake. So this new lake extends them beyond to almost to the western tiers, and then south to the near future Campbelltown. It was quite a lake. It had laid down vast stretch of sands and silts, which today are now rock, whose soils made the northern Midlands. Its total area exceeded 1,000 square kilometres. The Avondale volcanic dam that made it grew higher with the arrival of the outpourings of basalt and weathered dolerite masses. Meanwhile, to the north, the Batman Dam demolition continued, with the basalt blocks being dislodged into the banks of the Tamar along Whirlpool Reach. Now, with the second lake full, the valley and valley formed, let's turn our attention to Launceston and look west towards the dolerite tier that's holding back that second lake along with the Avondale volcanic dam. Here, the modern-day Prospect Vale is on the left and Hadspen is on the right. You can see the lake level creeping up and starting to finger into the valleys in the dolerite tier. Very close to Prospect Vale, the second lake occasionally quietly overlapped a saddle in the dolerite tier. And over time, it actually laid down a domed outwash fan of soils and silts, which is now under the suburb of Prospect Vale. However, there was a competing spillway near future Hadspen. This allowed a finger of the second lake to enter a fracture in the dolerite, so water crossed the crest of the tier at an altitude of 190 metres. The Hadspen fracture allowed more water from the second lake compared to that at Prospect Vale, where there was no fractures. The result? The channel grew deeper. It entered another fracture and another. More water flowed and more vigorously. The water from the second lake had finally crossed the tier and reached the edge of the Trevelyan Fault Scarp. A powerful waterfall developed at the scarp. The falling water undercut the dolerite columns of the tier. The parting and the columns allowed them to fall. In this way, the waterfall retreated upstream, getting lower and lower, leaving the gorge with its cataract bed, revealing the gorge as we know it today. You can see the direct evidence for this for the start of the waterfall with a 15-metre deep plunge pool that's carved directly into the dolerite bed of the river at Kings Bridge. This completed the diversion of all the North Midland rivers back into the Tamar Valley via the second lake. The excavation of the gorge probably took in the order of 3 to 4 million years, completely draining that vast water resources of the second lake. The second lake provided a continuous torrent of water. We are talking the volumes of water the equivalent to a continuous 1 in 200 year cataract flood that we experience today, endlessly racing through. The process, as mentioned, completely drained those vast water resources of the lake. What was left behind were the sediments and modern rivers, which form today's rich Tamar northern Midlands and farmlands. So let's zoom out again and see the big picture. So the surprising new conclusion is that the lake that made the gorge made the Midlands. Without the volcanic dams, there would be no lake, no northern Midlands, and there would be no Cataract Gorge. So if you have a look at Bob's research paper, you'll see that the main new conclusions from his study are: 1. Before the Evandale Dam, all the rivers converged and flowed into the Tamar under the future Evandale. 2. Without the Tamar volcanic dams, there would be no Cataract Gorge. Without the Evandale volcanic dam, there would be no Northern Midlands as we know it. Fourthly, the course of the South Esk River was not deflected into the gorge. Fifthly, there existed a spectacular 100-metre waterfall at Kings Bridge, gouging that 15-metre deep plunge pool directly into dolerite. And finally, the sixth point, after the Evandale Dam, all the rivers, except for the North Esk, converged and flowed into the Tamar through the Cataract Gorge. The tranquil Tamar Valley of today is a valley in valley, shaped by violent geological forces. The vast Midlands almost didn't happen for the combination of two volcanic dams, the first at 140 metre and the second at least 190 metres. It was not the South Esk that created Cataract Gorge. It was a lake behind the second volcanic dam that provided a torrent of escaping water with sufficient power to erode the gorge as we know it today. So, as you leave today and look at the Tamar landscape, we hope that you'll see it with new eyes, with a new perspective on its geological origins. Thank you.
Well, Tom and Bob, no doubt that's got all of us thinking differently. Thank you very much.